You've already learned about nuclear energy and how it includes nuclear fusion as well as nuclear fission. We're going to go a little bit deeper into nuclear energy, and we're going to learn how to calculate half-lives. So just remember from where we studied chemistry that an atom contains an electron cloud, so the electrons flying around the outside, and in the nucleus in the center there are protons and neutrons. Okay, remember that electrons are negative, protons are positive, and neutrons are neutral, and that positives and negatives attract towards one another, but like charges repel away from each other. So positive and positive want to get away from each other. Negative and negative want to get away from each other. Now it's a lot easier for the electrons to space themselves out so that they're not repelling each other because they have that electron cloud around the outside of the nucleus. But the protons are all housed within a very small space inside the nucleus. And so it's a lot harder for them to space themselves out to lower that repulsion charge. So radioactivity is the process of nuclear decay, which means that the nucleus breaks apart. So in these atoms that have a lot of protons in the center, a lot of repulsion pushing away from each other, those nuclei can actually break apart. They can actually repulse each other apart. And when that happens, it gives off a whole bunch of energy as well as some matter. Remember that isotopes exist, that an isotope is a version of an element with a different number of neutrons and thus a different mass. We learned about this back when we studied chemistry. Okay, an element has to have the same number of protons. That's its identity. But that same element can have different numbers of neutrons, giving it different masses. So we have hydrogen 1, which has a mass of 1 because it has no neutrons. We have hydrogen 3 because it has a mass of 3 because it has 2 neutrons, and so on. So a new term is transmutation. This is the process of one element becoming another element through nuclear decay. Okay, so when the nucleus decays and loses protons, it turns into a different element because it now has a different number of protons. Remember this is a nuclear symbol. We had a worksheet where we practiced using this. So just a reminder of all the information this provides. So this is a carbon because C stands for carbon. So we know we're looking at a carbon atom. The top number tells you the mass. So the mass of this particular carbon is 12. The bottom number tells you how many protons. So this carbon has 6 protons, which all carbons have 6 protons. But using the top and the bottom number, we can say, well, how many neutrons are there? If the total mass is 12 and there are 6 protons, then 12 minus 6 means that there are also 6 neutrons, because the mass comes from neutrons plus protons. Okay? All of this is a review from back when we studied chemistry. So what makes an element radioactive? It's all about the ratio of protons to neutrons. If there are too many protons in a space without enough neutrons to sort of go in between those positive charges, that's going to make it unstable. Because remember, those positive protons are going to want to get away from the other positive protons. So we need those neutral neutrons to add stability. Okay, so in small atoms, a stable ratio is 1 to 1. For every 1 proton, you have 1 neutron. But as the atoms get larger, they can have a different ratio. They can have a 3:2 ratio. So you can have 3 protons to every 2 neutrons. And that is enough neutrality to allow for some stability in those larger atoms. All elements that have more than 83 protons are radioactive. They are prone to decay. And almost all elements with more than 92 protons don't exist naturally in nature. They were made in labs, and very shortly after they're made, they decay because they're very, very unstable. When a nucleus decays, it can give off different types of radiation. There's alpha radiation. This is when it's actually a particle and energy that's given off. So it's 2 protons and 2 neutrons are released from the atom. This is essentially a helium atom is released because it has 2 protons, just like helium. Okay? And it has 2 neutrons, which makes its total mass 4. This means that it has a charge of +2. It's a +2 charge because no electrons are going with it, just the protons and the neutrons. So it is a charged particle. But it can be stopped by paper. So if it hits paper, it cannot go any further. It cannot go through the paper. Another particle is a beta particle. The beta particle is essentially a charged electron. And it has a charge of -1 because electrons are negative. This can be stopped by aluminum foil. Then we have gamma radiation. Gamma radiation is not a particle. It is an electromagnetic wave. So it does not have a charge because there are no protons, no electrons, so it does not have a charge. It is neutral. But it can only be stopped by concrete. So it can tear through paper, it can tear through aluminum foil and keep on going, but concrete is what stops it. Alpha particles are dangerous because they are large and charged. And because they are a charged particle, they can cause damage to your biological systems in the body. They cause cells not to function properly. So they cause all kinds of illness and disease. Beta particles, they're much smaller, but that also means that they're much faster than alpha particles, which means they can penetrate the body more deeply. And again, they are a charged particle, so they can cause damage to your cells due to having that charge. Now, gamma rays are the fastest. They travel at the speed of light, and they are usually emitted along with the alpha particles or the beta particles during decay. These are less damaging to the body because they don't have a charge, so they don't do as much damage to our systems in the short term. All right, so we're going to get to what we're going to practice with today, which is calculating half-life. So what is half-life? It is represented by a T with a little sub 1/2. And this is the amount of time that it takes for half of the atoms in a sample to decay. Half-life. So the lifespan of 1/2 of the atoms. Here are some examples of half-lives. So you can see polonium-194, remember that number is its mass of the atom, is 0.7 seconds. So this decays very rapidly. And then you can see some of them get longer. Carbon-14 has a half-life of 5,370 years. That's a very, very long half-life. Okay? And we can graph half-lives, and their graphs are going to be similar to this. So how do we calculate half-life? Here's an example problem. How much of a 20-gram sample of sodium-24 would remain after decaying for 30 hours if sodium-24 has a half-life of 15 hours? All right, let's analyze our problem and see what we know. Okay, so we know that we're going to decay for a total time of 30 hours. We know that one half-life is 15 hours. And we know that our original sample mass was 20 grams. Okay, so the first thing that we need to do is we need to figure out how many half-lives do we need to go. Okay, so how many half-lives? So if we start with a total time of 30 hours and a half-life is 15 hours, how many half-lives is that? Okay, we're going to do 30 divided by 15. 30 divided by 15. So do your total time divided by one half-life, and that tells you how many total half-lives. So we need to go for 2 half-lives. Okay? Then we start with our 20-gram sample. That was our original mass. So we do 20 divided by 2 because one half-life means that half of it decays, so we just have to divide it in half. So 20 divided by 2 means that after one half-life, we will have 10 grams remaining. But we need to go for 2 half-lives, so we got to do it again. So now we do 10 divided by 2. We have 5 grams. We have now done 2 half-lives. So that's as far as we needed to go. So we have 5 grams of sodium-24 would remain after 30 hours. Okay? So if you do not understand how to do this, please get into contact with me so I can help you, because it's time for your independent work. On your independent work, you're going to have 2 types of problems. You're going to have one where you work through just like this, where you have to figure out how many half-lives, keep dividing by 2 that number of half-lives to find your final sample size, and you'll also need to go in reverse and determine what the half-life is if you are given your beginning and ending sample. Okay, so if you need any help, please get into contact with me so I can walk you through the steps again.